Hello students, myself Ramesh Kothari welcome you all in the world of fermentation technology. This lecture is a part of MEICT project, an initiative of Ministry of HRD, Government of India. Today, we will focus our discussion on Ancillary component of fermentation media part 2, in which we will focus our discussion on the importance of inhibitors, inducers, oxygen and anti-foam agents in the fermentation media. We know that metabolic regulators play an important role. Several components like inducer, precursor and inhibitors, when added in the fermentation medium, help to regulate and control the production of product rather than support the growth of the microorganisms are called metabolic regulators. We will see now what are inhibitors. When some inhibitors are added to the fermentation media, it leads to the production of specific product. For example, glycerol production. In glycerol production, the production of glycerol depends on changing the ethanol fermentation by removing the acetaldehyde. In this fermentation process, the addition of a sodium bisulfate in the medium result in the formation of acetaldehyde disulfate, which is also known as sodium hydroxyethyl sulfite. Because acetaldehyde is not available for a long time for reoxidation of NADH2, dihydroacetone phosphate, which is also known as DHEAP, which is produced during the glycolysis, take its place as hydrogen acceptor, and the product of reaction is glycerol phosphate, which is converted to glycerol. Following table illustrate the application of general and specific inhibitor in several fermentation processes. For example, for the production of glycerol, sodium bisulfate used as an inhibitor. For the tetracycline production, bromide used as an inhibitor. Glutamine acid synthesis, penicillin is required as inhibitor. For the citric acid production, alkali metal and phosphate is used as inhibitor. For rifamycin B production, diethyl barbiturate is used as inhibitor. 7-chloro-6-dimethyl tetracycline is used for ethionine production. Generally, addition of inhibitors reduce the yield of undesirable product and simultaneously raise the yield of desired product. As reported by Gorovich and his co-worker and Jomke and his co-worker during tetracycline fermentation, the chlorotetracycline production can be minimized by the addition of chlorination inhibitors, for example, brominide. Phillips and Somerson reported the use of penicillin and surfactant during glutamic acid production to change the cell wall structure and increase the cell wall permeability for release of metabolite. Now, inducer. Industrially important enzymes are mostly inducible and induce in presence of an inducer. For example, amylases can be produced by incorporating starch or dextrine as an inducer. Likewise, polyunases and pectinases can be produced in the presence of maltose and pectinase respectively. Several substrate analogues can also serve as enzyme inducer. Following table summarize the example of industrially important enzyme inducer. For example, starch and maltose, they are inducer for RFI amylase. Maltose for polyunases. Yeast mannans act as an inducer of alpha-aminoacidases. Phenyl acetic acid used as an inducer of penicillin acylase. Various proteins are used for the inducer of proteases and cellulases. Cellulose used as an inducer of pectinases. Likewise, isovaleric traits used for the induction of nitrilases. Mostly inducers are substrate or substrate-like analog, but many times intermediate product produced during the process can also be used as inducer. Likewise, end products can also be used as an inducer. For example, maltodextrins can induce amylase and fatty acid induce lipase. However, the cost of many inhibitors prohibit their use as an inducer in a commercial process. Reviews have been published by Enstrup says that economic use of inducer affect the overall fermentation economics. A review by Enstrup and Demands state that anytime the cost of certain inducers are so high that it is not advisable to use them in a commercial process. For example, use of maltodextrin to produce amylase and fatty acid which induce the lipase. As reported by Peberdy and Wayne, a number of heterologous proteins origin to viral, human and animal, plant and microbial can be produced in yeast, fungi and bacteria. On the other hand, these heterologous proteins may produce some degree of toxicity to the host and may affect the stability of heterologous protein expression. Now, oxygen requirement. Oxygen play a vital role to control the growth rate and metabolite production of the product. The availability of oxygen in the medium may be influenced by several ways like fast metabolism, rheology and antifoam agents. First, fast metabolism. Due to high concentration of certain substrate which metabolize rapidly, for example, certain sugars, the culture may become oxygen limited because adequate oxygen cannot be made available in the fermenter and this lead to a high oxygen demand. Oxygen demands of the culture can be influenced by several nutritional factors. For example, glucose can be utilized more rapidly than the sucrose or lactose by Penicillium chrysogenum. When glucose is used as main carbon source, specific oxygen uptake rate is very high. The problem of oxygen limitation due to fast metabolism can be overcome by three different ways. These are by reducing the initial concentration of main substrate in the medium, by adding additional quantities of this substrate as a continuous or a semi-continuous feed during the fermentation, and by varying the composition of the medium. For example, by incorporating medium with lactose and starch like higher carbohydrate and protein which do not metabolize rapidly. Now, rheology. Each component added in the medium influence the viscosity of the medium and subsequently affect the operation like aeration and agitation. The viscosity of the medium differ depending upon the type of compound added in the medium. As reported by Tafil and Pinhao, the rheological behavior of the medium may change when polymer like starch and other related carbohydrate are added in the media. The rheological properties of the media change with degradation of polysaccharide. Now, antifoam. Almost all microbiological processes face the problem of forming due to constituents present in the medium or some metabolite which are produced by the microorganism during the fermentation process. As reported by Shugler, media supplemented with protein-rich component like yeast extract, meat extract, constip liquor, soybean meal, peanut meal, and pharma media cause the problem of foam. The denaturation of proteins present in this component denature at the air-broth interface and result in the formation of a very thin skin which does not rupture easily. The foaming may produce considerable effect during the fermentation process. These effects are taking away the cell from the medium. It may result in the autolysis of the cell. Due to lysis of cell protein release, and this lead to increase the stability of the foam. On long way, it may reduce the working volume of the fermenter as oxygen exhausted gas bubble circulating in the system. The foaming also produce variation in bubble size, lesser mass and rate of the heat transfer. Due to interference of foam at sensing electrode, result in inaccurate monitoring and control, which ultimately lead to generate invalid process data. And foaming also produce some biological problems like cell deposition in the upper part of the vessel. As fermenter becoming wet, it may create problem of sterile operation with the air filter exit and loss of product due to microbial infection and drainage of the medium. Following are the pattern of foaming which take place during the fermentation process. The constant level of foaming occurs throughout the fermentation process. In the beginning due to medium component and afterward due to microbial activities. In the beginning, you will find a steady fall in the foaming which later on remains constant. Initially it is due to medium, but thereafter there is no later effect caused by the microorganisms. The foaming decline to some extent in the early stage and then rise. The major effects are caused by microbial activity and very less effect caused by the medium. The fermentation process has a low initial foaming capacity which rises solely due to microbial activities. During the fermentation, a more complex pattern of foaming may also take place due to two or more patterns as described above. There are many ways to cope up with the problem of excessive foaming. Use of defined medium for the process and alteration in some of the physical parameters like pH, temperature, aeration and agitation. Second, using suitable anti-foam agents. Third, installing a mechanical foam breaker at the head space of the fermenter. Anti-foam agents are surface active agents. It reduces the surface tension in the foam and destabilize proteins by forming hydrophobic bridge between two surfaces, by displacing the adsorbed protein, and by spreading it rapidly on surface of the thin film. There are various properties of an ideal anti-foam agents. These are: it should disperse rapidly on an existing foam and have fast action. It should be active and effective at low concentrations. It should be active in preventing new foam formation. It should not be utilized by microorganisms. It should not produce toxic effect on microorganisms. It should not be toxic to human and animals. It should not create trouble in the downstream processes like extraction and purification of fermentation product. It should not create any hazard while handling. It should be cheap and easily available. It should have no effect on transfer of oxygen during aeration, and it should not be heat sensitive. There are several examples of anti-foam agents. These are alcohols, esters, fatty acids and its derivative, mainly glycerol. For example, cottonseed oil, linseed oil, soybean oil, olive oil, castor oil, sunflower oil, rapeseed oil, and cod liver oil. Other anti-foam agents like silicones, sulfonates, oxygelines, polypropylenes, glycols are also frequently used in many fermentation processes. These anti-foam agents are generally added at the time of foam formation during the progress of fermentation process. Due to low solubility of several antifoam agents, they are added with various carrier molecules like castor oil, lard oil, or liquid paraffin, which may be metabolized and influence the fermentation process. The amount of antifoam agents to be added in the fermenter should be as less as possible because high concentration of many antifoam agents interfere the process of aeration by reducing as much as 50% oxygen transfer. When oxygen transfer rate is affected by the addition of certain antifoam agents, the best possible alternative way to control the foam is setting up an mechanical foam backer in the vessel at the top of the airspace. As reported by a group of scientists, foam control in the fermentation industry is an empirical art. The selection of antifoam agent vary depending on design and several operational parameters of a fermentation process. This is all about operational parameters of a fermentation process. This is all about ancillary component of fermentation media part 2. Thank you very much and have a good day.